Hello everyone, my name is Pano Georgiadis. I'm here to discuss today my technical walkthrough of a TIAGo robot pick-and-place controller implementation. The system demonstrates autonomous object manipulation using a behavior tree architecture in the Webots simulation environment. The controller enables the TIAGo robot to locate, grasp, and transport 3 jars from a kitchen counter to a designated table through a combination of computer vision, inverse kinematics, and reactive navigation. The key components of this implementation include a hierarchical behavior tree for task orchestration, sensor fusion for precise object localization, advanced inverse kinematics for arm control, force feedback based grasping, reactive obstacle avoidance, and a state-based navigation. So let's examine the code and technical implementation in detail before moving on to the video demonstration. The system architecture follows a modular design pattern with the behavior tree as its backbone. Some of the key imports are, of course, py trees for that behavior tree. The ikpy Python library is used for inverse kinematics, also for calculating where the end effector is on the joints. URDF parser is used to parse the robot URDF file, which is a file that contains all the information of what is on the robot or what makes up the robot's body. So that would show all the joints of the entire robot, all the joints that you would need in the arm, their minimum and maximum rotational positions, and also the height of things. So a big thing, you have to calculate where certain things are on the robot's body in order to use that calculation or offset. For example, the camera in the robot's head, you would have to figure out the torso lift position, as well as where the camera is located and the height of the robot in its head in order to correctly calculate the location and the height, the Z parameter of any objects that you're recognizing. The initialization phase establishes the robot's hardware interface and configuration parameters. In the imports from the controller, we're importing supervisor, which is used in when you're working with Webots in order to import the robot and actually initiate a lot of its hardware. Here you're initiating the joint limits, and then this is creating the inverse kinematics chain. You're starting with the base link, even though you're not controlling the base link. Well, for this purpose, we're not controlling really the base link. We're controlling the torso for some things, but not necessarily for arm grasping. But what you need to do when working with the ikpy library is you need to list the joints in concession of the beginning all the way to the end. What it's going to do is it's going to end up placing its own end effector after the last position, which for this example would be the wrist tool link front joint. And basically what it's doing is, with that end effector in mind, it will calculate where it needs to position all of its arm joints in order to get that end effector exactly where it needs to be in order to grasp or, for whatever use purpose you're using. So like I said, the initialization creates supervisor instance for accessing Webots functionality, extracts the URDF for kinematics calculation, and then we're also defining some constants here, just minimum and maximum motor speed, and then an angle tolerance. The angle tolerance is for precision of the rotational alignment. The robot's actuators and sensors are systematically initialized with appropriate time steps and measurement ranges following a consistent initialization pattern for reliability. Here we're creating the IK chain with all of these base elements. It's a very critical aspect of the implementation is the advanced inverse kinematic system. It enables precise positioning of the robot's arm. Like I said, based on the end effector for object manipulation. Inverse kinematics solves the problem of given a desired end effector position in a 3D space, what joint angles are required to achieve this position. It's a very complex mathematical problem, and it's due to multiple possible solutions of redundancy because you're working with an arm that I believe it's 8 degrees of freedom. To get to one point in a 3D space, you can actually move your arm in multiple positions. Say you have something in front of you like this, well, you can also reach it by going like this. And that's a big issue in calculating inverse kinematics. Also, joint limits that must be respected of all the different joints of that make up the TIAGo robot's arm. And then singularities that can cause instability, and then the need for a smooth, natural motion. Robots are basically computers. When you tell it to go to a position, it goes to exactly what you tell it to do. And because of that, there's always an issue with making things more smooth and natural in order to make the arm as effective as it possibly can be while attaining the end goal. So like I said, this creates the 15-link kinematic chain with active joint masking, which is crucial for TIAGo's unique arm configuration. The active link mask parameter specifies which joints in the chain can be actively controlled, improving solver efficiency and solution quality. And then the IK solver integrates joint limit enforcement to prevent physical constraint violations, initial configuration optimization for stability, which you'll see in the constant of the prepare arm for movement, and then the orientation constraints for appropriate end effector alignment, as well as numerical optimization with configurable iterations and precision. And then as you can see here, we are creating the IK chain and initializing the motors and sensors. And then we are just defining and mapping special sensors with special names just to make it easier for us. Here for part name and part names, we're basically initializing all devices. And then we're getting a summary, just making sure that everything has been initialized, the part names, and then the number of motors and the number of sensors initialized. For this robot, the number of motors that we are initializing, we want to make sure that the same number of sensors are initialized. So if there's 8 motors initialized, there should be 8 sensors, and so on and so forth. We are then initializing the camera with proper resource management. A lot of what set me back in completing this, and I felt like should have been a shorter amount of time, was the limitations of the Webots environment in regards to the threshold of when it force closes due to too much CPU or GPU processing that it's taking up, which I'll also get into a little later. But the only reason for this function to initialize the camera like this is just to make sure that it's initializing the camera correctly. I had a lot of issues where the camera was not working correctly. So here we're enabling the camera, enabling display, GPS, compass, LIDAR. We're enabling force feedback from the positional sensors on the gripper left finger joint and right finger joint, initializing the wheel motors, and then, getting into the starting position, lift position, place position. These are positions that I found made movement for the TIAGo robot more reliable. Instead of having, as you can see, when the robot is introduced into the space, it has it fully extended to the right, making it extremely bad at traveling around the environment, moving to objects, moving to waypoints. So this starting position just gets the arm out of the way in order to make travel easier. It lifts the torso joint because, as you can see, the robot is lower than the counter at this point, and then puts the arm in a somewhat close to torso upward position in order to make movement in the environment a lot easier. This lift position is being used once we have the jar in the grippers of the robot. It's using that lift position. Once it's lifted and verified, or once it has grasped and verified the jars, we want to make sure that we're lifting in a position that brings it somewhat closer to the robot with the same thought process as the starting position, just to make the movement of the robot a lot easier throughout the environment. The place position is used to place the jar on the table correctly, and then we have table waypoints. We're moving down -y, and then from where the location of the jars are, you'll see, and then we're moving over to the left or in a -x in order to move to the table, and that's just ensuring that the waypoint, that the direction of the robot and its arm is facing the table. You could have done this in multiple different ways. I just found that this was the most simple way. You just put a location that is south of where the robot is, and then towards the left of the robot, and that ensures that its arm ends up over the table. The sensor fusion system integrates data from multiple sensors to create an accurate world model. This camera to world coordinates, what it does is it's a function that handles critical transformation from camera relative object positions to global world coordinates. It's applying a rotation based on the robot's compass heading, a translation based on the robot's GPS position, height correction accounting for torso ellipse position, which I explained a little earlier, and then empirical correction factors to compensate for systemic errors. The sensor fusion accuracy is critical for reliable grasping, as errors in object position estimation would propagate through the inverse kinematics solver, thus potentially causing grasp failures. This function, I've gotten it to be almost exactly spot on to the actual location of any object that it's recognizing, which is pretty impressive, and I'll show you that once we get into actually using the controller. The calculate approach offsets is used as it's used to calculate the approach vector based on the robot to target relationship. A lot of that is because the robot forgets exactly its orientation on the map, and what you're doing is you're getting the approach vector of the robot based on the compass, and then you calculate based on the compass of the robot the vector from robot to target, and then what it would do is you would calculate any offsets needed in order to calculate the inverse kinematics of arm position in order to grasp the object. Now what we're doing here is we are actually calculating the inverse kinematics. It computes joint angles required to position end effector at target location. It uses the ikpy chain with joint limit constraints and initial position clamping for a reliable solution. And yeah, I mean, thankfully the ikpy library exists, because at one point I was getting frustrated why it wasn't working. I'll get into that later, but I then personally tried solving inverse kinematics for the joints, and it is an extremely long and annoying process. Thankfully, this makes it so that we don't need to hard code all of that inverse kinematics problems. You then have a few more helper functions: normalizing angles, the angle difference. This is just used for, I believe, moving to waypoint, moving to object, and then target position. What you're doing is you're making sure that when we recognize an object, whether through the enhanced object scan recognizer or through scanning, that you're saving its location on a blackboard, and then the get target position is carrying that position blackboard to be used throughout the behavior tree. The last helper function is the create movement with avoidance. This is used with the LIDAR in order to avoid any objects in its way when trying to move to an object or move to a waypoint. The LIDAR works relatively simple and easy. Let me just show you. So the LIDAR is in a weird position on the TIAGo robot. It's on the base. It has a 240-degree field of view centered at the front. The problem is that because of this, sorry, I'll just go back. Because of this, you're actually hitting the robot in on the left and right side, and because of this, we're ignoring about 25 to 30 LIDAR ray paths. For some reason, the point cloud doesn't want to show at the moment, but yeah, so it's pretty much, it's hitting the far left and the far right of the robot. So you need to make sure that you're ignoring both the far left and far right LIDAR paths, LIDAR detection, in order to avoid false positives. And then what it's going to do is it's going to choose whether on the left and right side of the object that's causing the obstacle or the block, it's going to see whether the left or right side has less or more space blocked, and the side that has less space being blocked, it will choose to go that side in order to go around the object and go to its waypoint or object. Let's see, the enhanced object recognizer is, this is the computer vision object detection and localization behavior. It's a object detection system that uses a multi-strategy approach, and you'll see it's implemented through the behavior trees. This node, it processes the camera's recognition data, filtering for jar objects, transforming their positions to world coordinates using our sensor fusion system. And yeah, I mean, if you look, for example, on the camera, because of the enhanced object recognizer, we're getting the name of the object, its ID, relative position, and then color. You could also use object recognition with the camera that's mounted in the TIAGo robot for color recognition if you wanted to. I found it was easy, since we're just going after jars, to just go by the name of the object. If it is a jam jar, honey jar, things of that nature, then it would get recognized and put that on the blackboard and know, okay, well, we need to go there and grab that. Another really cool thing that I implemented that solved a lot of problems was the comprehensive scanner. When direct recognition fails, the system falls back to a comprehensive scanner. This implementation uses a state machine approach. It methodologically rotates through 8 different angles at 45-degree increments, attempting recognition after each rotation, provides 360 coverage to locate objects that might not be visible from the initial position. It also lifts the torso to its highest position that it can be. For this scenario, we don't necessarily need that. I just wanted it to be something that could be reusable. Basically, the thought process is, if you're scanning for objects and you can't recognize an object, lift the torso of the robot as high as possible to get a better point of view for scanning. And then what we're doing is we have a timeout. If it's not recognizing an object, then it continues to rotate until it completes a full scan. And then at a full scan, it will exit and say that there were no objects recognized. If it does recognize an object, it'll say object recognized after rotation, and then it'll put that as an object on the blackboard that it needs to go and grab. Moving on to our grasp controller. This is a robotic grasping controller with force feedback verification. When approaching, it will make sure that the gripper is fully open. And then it also has verifying as soon as the gripper closes on the jar, or where it thinks it should have a jar in between its gripper joints. It then verifies that that it's not fully closing. This could be either via force feedback or via where the open position is 0.45 on the gripper joints. The closed position would be 0. So if it's not able to reach 0, then clearly there is something in its hand. Now, the navigation system, it implements a state-based approach for proportional control. This implements GPS and compass-based path planning, dynamic speed control based on distance, obstacle avoidance using the distance sensors, and arm pre-positioning when approaching the target. You want to make sure that when you're moving to an object, you're not calculating the inverse kinematics exactly in front of the jar, because that way, when it goes to adjust its arm, it will, it could hit a counter, or it would knock down everything on the counter, knock away the jar, things of that nature. So you want to implement, what we did here, I chose a 1.28 meters as a arm adjusted distance. It's close enough where the robot has the object directly in front of it, and far enough where it can adjust its arm freely and smoothly in order to get it in a position where it needs to grab the jar. A very close distance is at 1 meter, so that pretty much says, okay, well, we're extremely close now. We've calculated the inverse kinematics at this point. Let's make sure that we approach as slowly as possible to prevent oscillation and wobbling of the robot, in order to make sure that the jar ends up directly in between its grasp. Especially in Webots, when you're doing it in an environment like this, the oscillation or anything with you can find multiple times if you press play on the scenario, 90 out of 100 times it'll work, but then there's 10 times where for whatever reason there's motor and movement oscillation, and it causes the gripping to fail or the arm to be off just a little bit where it's not going to work. So I really wanted to make sure that we slow down once we get really close to the object in order to prevent all of that. And yeah, I mean, you can see that, the state machine, it has orienting, which would be the rotational alignment toward the target. Then it has approaching. For the main movement phase with distance-based speed control, then it has stabilizing for motion dampening to ensure precise positioning. Adjusting arm is the coordination of the arm movement during the final approach, and then the final approach, which is precision positioning with slow controlled movement. Move to waypoint. This is similar to move to object. It's just a lot more simplified. It's simple proportional control for both linear and angular velocity. Waypoint sequencing with distance threshold, and then a timeout protection in case LIDAR does not work in avoiding an object, or if the arm gets caught somewhere or anything like that. It's just a safety timeout mechanism. As you can see, where, same thing, initializing the motor's velocity, getting the compass heading, the GPS, and then the current waypoint, and then calculating the velocity based on error, and so on and so forth. Manipulation behaviors, the inverse kinematics based arm motion planner. This is one of the most important aspects of autonomous grasping in the controller file. It's a manipulation system that combines inverse kinematics and force-based grasping. The arm control implementation uses inverse kinematic solution with approach vector offsets for reliable positioning. And then you can see this pre-grasp position is in there. This was through trial and error and much frustration. I figured out that you cannot just have the arm wherever you want it to be and then calculate the inverse kinematics when doing it multiple times in an environment like Webots. You want to make sure that the arm is in the exact same starting position each time it goes to approach an object, ensuring that when it's calculating the inverse kinematics, that it's that the end effector is going in the exact position that you want it to go into, and that there's no leeway for any joint positioning errors. Move to position. This is a lot more simpler than moving the arm IK function. This move to position is just a multiple joint coordination with velocity control and positional feedback with tolerance checking. What it does is, if you say to move the arm to a safety position, you give it its target joint positions and it moves to those positions. And then it has progress monitoring to detect stalls and obstructions, and auto completion on timeout with success estimation. Just letting me know, that we're going into this position, we're in this position now, everything's okay. We're not in this position because something happened or that it's a timeout, and we'll consider it a success. Open gripper is just a simple function that tells the gripper fingers to carefully open and release whatever object's in its grasp. And then it also implements a timeout mechanism to handle cases where mechanical obstruction could take place and might prevent fully opening. In that case, the timeout would not cause the behavior tree to fail or the robot to just be stuck. It would try and open if something was blocking it for whatever reason. It would then initiate its backup sequence, which hopefully would release it from its grasp. Another important thing when lifting, I implemented a lift and verify class. Its functionality is that it will coordinate joint motion for vertical lifting with continuous force feedback for validation, and then a timeout protected motion execution. What you'll see is that it will grab the object, and then the grasp controller will say, okay, I have something. It will then go into the lift position, and when going into the lift position, I wanted to make sure that we're verifying while moving from the lift position that it doesn't accidentally drop whatever object it's grabbing. It wasn't necessary, but it's just something that I thought would make everything a lot more autonomous and better. Next, we have backup after grasp. This is just a safe backward movement after successful object grasping. You could choose to go directly to waypoints after grasping an object and verifying that you have it. I just found that the backup and grasping just makes everything a little more reliable in an environment, and would make this controller able to be used in other environments as well, not just in this kitchen type environment that we're working with today. Now we have some decorators that simply just check the hardware status, motor controllers, position sensors, camera, subsystem, and navigation, the GPS and the compass, just making sure that everything is working as is. Most important, most important part, of course, is the behavior tree construction. It uses a modular approach, and the implementation uses PY trees compositional approach to create a hierarchical behavior structure that enables sequential execution of task phases, fallback mechanisms for robust operation, memory persistence for state tracking between ticks. It's modular and reusable for a lot of the behavior components, and it's gives a clear visualization of the system state during execution, which you'll see when it's printed. The tree structure follows the compositional design pattern where complex behaviors are built from simpler components. The key composite nodes are sequence nodes. They execute children in order, requiring all to succeed, and then selector nodes, which try children until one succeeds, providing fallback capability. The behavior tree's memory parameter, memory equals true, is particularly important. It allows nodes to remember their state between ticks, enabling efficient resumption of operations. Oh, and one thing that I did want to explain is the Y offsets. These Y offsets are used after calculating the inverse kinematics of arm position for the end effector. No matter how hard I was trying to get everything to be perfect in Webots, I'm not sure if it's a limitation due to the processing, the lack of the ability to set more processing for Webots. But no matter what I was doing, these offsets are needed in order to ensure that the Y position, which would be left or right of the jar, is exactly where it needs to be. This could be due to oscillation or arm oscillation. I mean, there's multiple joints that could be oscillating and things of that nature. And whenever I tried to make things more accurate, more precise, I was having Webots constantly crash. No matter what I was trying to do, it wouldn't allow me to make it more precise without crashing. And I highly doubt it's my system. I'm running on a 3090 GPU. I use machine learning projects all the time. but Webots, for whatever reason, just can't handle it. So the offset there is just simply to make sure that the Y positioning is on the jars. And sometimes this offset isn't even consistent, which is another weird thing. I can have it play 10 times, and 8 times out of 10, this offset will be right. And then the other 2 times, for whatever reason, the first jar will be perfect. The second jar, the offset will be off. Third jar, the offset will be way off. I've tried working with it, for off and on for about a week, and that's just where we're at this point. Lastly, we have a runtime monitor. Just tracks the joint position history, navigation trajectory, sensor consistency, and things of that nature. And then, of course, the main execution loop, which puts everything together, initializes the behavior tree and all of the components and hardware of the robot, and then gives us some debug logging just to make sure that everything is running correctly. So as you'll see when I'm about to play this, the system achieves impressive performance metrics. Its object recognition success rate is greater than 95%. I've had very, very few times when it's failed. Most of the time was due to oscillation. We are scanning a little quickly before changing angles, but I found that it gets the job done over 95% of the time, so why slow it down? The grasp success rate is at 100% because we have not only the first grasp check, but we also have a lift and verify check as well. Our navigation accuracy is plus or minus 0.08 meters. Our path efficiency is around 90% for displacement over total distance. And then we have that force feedback consistency for the gripper fingers. Pretty much consistent across the board for each jar. The controller demonstrates reliable operation across multiple test scenarios with successful detection and transport of all 3 jars. And yeah, let's get into showing you how everything works. So as you can see, when we first initiate, we should get the initiation of and what did I do here? I think I might have accidentally hit something. Yep. Let's do this for now just to see what we're going to get. All right. So for some reason there was an issue enabling the LIDAR. That was the first time I ever had that error, so I'm not exactly sure what the issue was. But either way, I'm just going to show you how we get all the jars at the moment. As you can see right in the beginning, we're getting a chain created with 15 links of all of the motors in the robot that are picked up from the URDF file, and then we're getting a matching number of motors initialized, number of sensors initialized, getting the camera, GPS, everything is initializing successfully, and then we're getting this safe position in progress, which you can see right here. It's moving in an upward position out of the way of everything, raising the torso hinge joint. And now, if you saw that real quick, it actually found 2 objects, one at 192. Let's get this over here so I can show you the precision of the camera. We're getting one at 1.92, one at 0.49, and one at 1.7 and negative 0.2. What it's going to do if it detects 2 objects is it will choose the object that's closest to it, and then add that to the blackboard. So stored target position and object jam jar on blackboard. It will then go into the prepare arm to move to object position in order to calculate inverse kinematics from the same position each time, using target position from Blackboard and starting GPS positioning in order to move to waypoint. Once it gets to that 1.23 meters, it should start calculating the inverse kinematics, which it did successfully right here. Attempting IK for final target, and then IK solution found successfully. Started arm movement with angles, and then all of these angles were calculated from the inverse kinematics. And as you can see, it is pretty much spot on. We then have grasp, which you can see contact detected, grasp successful, lift sequence, and then object securely held. So the lift and verify worked. It'll then go on to move to the table. Drop it on the table, and then it should go back home. Now this is really cool. Once it gets to the home position, it'll initiate the recognition. If it doesn't see anything within 3 seconds, object recognition timed out, starting comprehensive scan with 8 angles. I'll let this play in real time just to show you how good it works. And there you go. As soon as it came into view, we have found object honey jar. Camera sees one object, it gets its location, puts that stored target position on the blackboard to be used, and then starts going into the move to arm position to start to calculate the inverse kinematics once it gets 1.23 meters, 1.28 meters close. Same thing, we have a success for calculating. It's then going to do a final approach movement very slowly, grasps the jar, lift and verify, back up, move to the table. Now we have the final and third jar. Same thing, doesn't recognize an object right away after 3 seconds. It then moves on to the comprehensive scanner. And then you'll see right as it goes into view, there you go, recognizes the object, figures out its location, puts its arm in a position to get ready to calculate the inverse kinematics, moves to the target position at 1.28 meters away, calculates the position it needs to be in, grabs the jar perfectly, it verifies that it's grasped it, backs up, lifts and verifies that it still has it, and then goes to the table. And there we go. That is success. Everything worked. All waypoints reached. Behavior tree completed successfully. And I actually, while that was playing, my brain figured out that this enabled LIDAR, it stopped working actually because while I was trying to show the LIDAR paths, I somehow deleted the LIDAR from being there altogether. I'd have to go in and reload from a different save point. Not sure how that happened, but that's why we were getting that error. But yeah, as you can see, it successfully does its job of grabbing all 3 jars. And if you feel like checking out the code or anything else, you can feel free to go to my GitHub. I have a full report write-up on it, explaining things in detail. And then you can also see the controller file, the robot URDF, any images that you would want to see for how it worked, what it recognized, anything like that. And then if you want to play around with it, you know, you can fork and start messing around. Maybe you can get it to detect other objects, which would be relatively easy to implement. So yeah. Thanks for listening. I hope you enjoyed, and